Hello everyone. In this video, we will try to learn about the different observability criteria, and we will focus on the first test of the observability criteria. And in the criteria, there are sorry. First one is the Gilbert test for the observability. Second one is the Kalman test, and third one is the factor cancellation test, and fourth one is the PBH Popo Balavich Hautas test. Popo Balavich Hautas test, right? So we will discuss one by one in this video. We will cover the first one, that is the Gilbert test. Okay, so in the previous video we have already established the concept of the observability, and it is once again I am saying, if you have not visited, or if you have not gone through, or you have not revised the previous video, so it is very difficult, it will be very tough to understand what we are going to discuss today. Okay, so it is the best practices for the better understanding. It is my suggestion to go to previous videos and learn them first, and then it is start with this video. So I'm just starting in this video for the Gilbert test, right? For the Gilbert test. Okay, Gilbert test, in the controllability we already have seen with the help of the Gilbert test how we have developed this criteria. This criteria basically depends upon, you can say, the visualization. Okay, visualization of the figure, from the figure. So you can see here in this two picture first and two, one and two. Here the in the second picture or second figure, the first state variable x1s is not connected with the output yt. However, in this figure 1, all the state variable including x1, x2, x3, all the state variable, this three state variable, we may obtain here at the output, or you can say we can determine the all the state variable with the help of this output. And therefore the equation has been written here as y equals to kx, and in the k2 x2s and s3s is only able to, you can say, we can find out. However, the x1 can not be determined, and therefore this is not completely observable. And if you're writing the equation, I'm just writing both the equation for the equation figure 1 and figure 2. So for figure 1, you can write here, since each of the state is connected to the output, and therefore the output equation is, you can write here, x k1 sorry k1 k2 k3 into simple x. Okay, this is equal, let's say this, I'm just writing this equation number 1. And for 2, for figure 2 the state variable x1 is not connected, and therefore the output equation for the figure 2 is, you can write here, y is equals to 0 k2 k3. K2 k3 are connected with the output. However, the x1 variable is not attached, and therefore the coefficient of this one is 0. Okay, and you can right now say, based on this, this system is, this represent, you can say, the observable system. This represent observable system, right? Observable system. However, this represent uh, non-observable, unfortunately, and unobservable system, right? So conclusion is this one. You can make a conclusion here. And that conclusion is very simple. Conclusion is very simple. And you can write here, you can simply write by comparing equation number 1 and 2, it can be observed that it can be observed that for a system okay, and once one more important thing is here, I have already mentioned in the previous video. This representation is nothing but this figure number 1 and figure 2. Figure number 1 and figure 2 are in the form of a diagonal canonical form. Okay, simply it is a diagonal canonical form. So first of all, if you want to test, if you want to find out the system is either observable or non-observable, it means you have to first represent the system, the model equation, the state equation in the form of the diagonal canonical form. So the system, by comparing equation number 1 and 2, it can be observed that for a system represented in, okay, for system represented in diagonal canonical form, right? Diagonal canonical form. If the model equation is not in the diagonal canonical form, then you have to first transform, you have to convert into the diagonal canonical form, and it can be observed, and in the system, this system is observable when or you can say it can be observed that for a system represented diagonal form to be completely observable, it's the system represented by the diagonal canonical form is said to be completely observable if and only if the output matrix, it means it should not contain any zero. If it can contain zero, it means you are not able to, if one of the state variable is not connected with the output. It means simple. So completely observe the output matrix should not have any zero. And this is a very important line, and this is nothing but it is known as the Gilbert test criteria. I hope you understand these things. Okay. So if the system is not converted, if the system is not transformed to the diagonal canonical form, or the system is simply represented in the ordinary form, then we have to first apply the transformation rule. It means the output equation y equals to, have to write cx, right? Y equals to cx is to be transformed, right? Is to be transformed first. If the system is not represented in the diagonal canonical form, then y is equals to cx is to be transformed into the diagonal form, right? Diagonal canonical form. That can be represented. And how it is transformed, we already discussed. We have already discussed how a system can be converted or can be transformed into the diagonal canonical form. So the simple fundamental is here. You are writing the transformed equation is simple CPZ. Please visit the previous video so that you can understand it. Okay. So y is equals to CPZ. Okay. And the system, the transformed equation is CP, and Z is the variable, right? The system is completely observable. The transformed equation is this one. So now this equation is said to be completely observable, or the system is completely observable, okay, because your C matrix converted into CP, right? Observable if and only if any column of not here C matrix, okay, you have to check the CP matrix now, okay. If any column of matrix CP, okay, is not with all 0. Okay, 0 element. And this is the case for the Gilbert test, observability test. Gilbert observability test. You can check. Okay. Now third case. Okay. So first possibility is the model equation represented in the diagonal form. If not, then you have transformed. Okay. And third case is if the system has the repeated eigenvalue, then how the observability test can be employed with the help of the Gilbert test. So for repeated eigenvalue, okay, for repeated eigenvalue we will see. And you know, for the repeated eigenvalue, we already have established the concept if the system is if the system have, you can say, no repeated eigenvalue or the distinct eigenvalue, then the system is represented in the form of diagonal canonical form, right? Or the system may be, any system will transform to diagonal canonical form. However, if the system has repeated eigenvalue, then the system is represented with the help of Jordan canonical form, right? Jordan canonical form. Okay? Jordan canonical form. So you can write here the system transformed to Jordan canonical form, right? To Jordan canonical form. Okay? Jordan canonical form. Once again, I am saying we already have discussed. If you don't know about the Jordan canonical, how the system is going to convert to the Jordan canonical form, please visit the previous video. Once again, okay. So let's say we have a third order system. Let's say we have the third order system. Just I am taking an example, third order system, and considering with two repeated you can say eigenvalues or poles. Eigenvalues, right? So try to draw the Jordan canonical form third order system where the two eigenvalues are repeated. Okay, so I am drawing the Jordan canonical form. Okay, and you know how this is going to represent, right? Minus lambda 1. Okay, I did nothing but the s plus lambda 1, right? Right. This is x2 dot, right? Come to the next. Come to the next. That is the again. Sorry, my mistake. Lambda 1, because this is a repeated root. Okay. This is the x1 and x1 dot, and here it is the k1, and you can say here this is the k2, this is the k2 for the second state variable, and okay, it is, I think, this one the integrator, and let's say the second or third pole is lambda 3. Okay, and then k3 is attached with all the output. Okay, we have taken here the first, second, and third. Okay, and this one is we have yt, and this one is your ut. Okay, fine. So this figure is represented in the form of Jordan canonical form. Why? Because roots are repeated, or the eigenvalues are repeated, or you can say the poles are repeated. Okay. So from this figure, you can clearly observe that x1 is linked with the output, this state variable directly linked with the output. However, x2 is not linked. Okay, so you can say here this state x3 and x1 and x3 you can obtain at yt, or you can say in opposite, yt may be x2 and x3 may be calculated with the help of yt, or the output. Okay, however, the k2, if let's say if x1 is not linked, let's say consider if x1 is not linked with the output for the moment, let's say for some moment, let's say this is disconnected. So if x1 is not linked with the output, it means x1 is not observable, right? X1 is here not observable. Fine. X1 is not observable at the output. X1 is not observable at the yt, right? Output. X1 is not observable. X1 is not observable at output yt if x1 is not linked. If x1 is not linked, remember. But so it means it is the unobservable system. Simple. It is not completely observable. It means it is not completely observable. Not completely observable. Remember, not completely observable. Next possibility is let's say k3. Let's say this x3 is not linked. This is linked. This one is linked. Okay. This one is linked. Sorry. My drawing is very poor. That's why. Okay. This connection is now, let's say, disconnected. So again, you can say x3 is not absorbed at output yt, and since x3 is not linked, and therefore it is not observable completely. Again. And what about the third case that I am going to discuss here? What about the x3? Let's say this is not connected. This is not k2. The outcome, the output from the x2 that is attached here is not connected now. This is disconnected. Let's say k2 is 0. K2 is 0. K2 is, let's say k2 is 0, but not k1 and k2. K1 and k2 is not 0. Right, 0. What it means? It means you can observe both all this state equation here, x1, x2, x3. x2 is measurable indirectly with the help of x1. With the help of x1, you can measure this that indirectly, right? And therefore, the system is observable. Still, k2 is not connected. Still, k2 is not connected. Okay, so we can write here. If k2 is 0 but not k1 and k3, okay, or first consider for the k1 only, but not k1, okay, but not k1, you can write here both x1 and x2 can be determined, right? Determined. Hence, if k1 and k3 are not zeros, the system is completely observable. What it means? It means, okay, first we can write here for the system for the system to be completely observable, to be completely observable, it is necessary, it is necessary that both K1 and K3 should not be 0, right? Should not be 0. Whereas K2 can be 0. So what is the conclusion? How now we are going to develop the concept? What now we are going to define the definition for the observability in the case of the repeated eigenvalues, or the system may be system represented with the help of the Jordan canonical form. Okay, so I am writing the you can say step by step conclusion here, or in the form of summary. You can say if a state model is transformed, is it transform into diagonal form. First case, the case is the diagonal form. You have to first convert the diagonal form or the Jordan canonical form. If the eigenvalue is repeated, then it means you have to convert it into Jordan canonical form. And if the root is not repeated, then your system is converted into the diagonal form only, or diagonal canonical form. Okay, so you can say the system is completely the transform system. You can say the transform system is completely observable, or if what are the condition? First, for the diagonal form, no column. We already developed the concept, we already established no column of CP that correspond to distinct eigenvalue, right? Distinct eigenvalue consist of all 0 elements, right? Second case, no column, ऐसा कुछ 0 element का होना नहीं चाहिए, right? In the second case, no column of CP that correspond to the first, listen carefully, first row of each Jordan canonical form of all 0, because K2 K3 may be 0, K2 may be 0. The first from the figure, from this figure you can see still the K2 is 0, the system is observable, right? So you can write here the now column of the CP that correspond to the first row of each Jordan block consist of all 0, right? Consist of all 0, and other, it means it is the distinct. For the distinct, we are discussing about the distinct. Okay, and where it is repeated, that means all other element and all other columns. Okay, columns corresponding to other eigenvalue do not have all 0 elements, and this is the fundamental of the Gilbert test. In the last, I am just taking one example. This is the x dot is equals to, let's say, 0 1 8 minus 2 x plus 1 1 u, and y is equals to 4 1 x. Now we have to test with the help of the you can say the Gilbert test, right? Gilbert test. So with the help of the Gilbert test, you have check the observability or confirm the observability. Check the observability or comment on the observability, right? So first of all, you have to find the eigenvalue. Eigenvalue you can find lambda minus 1 minus 8 and this becomes lambda plus 2, right? And equal to 0, so it will give the lambda square plus 2 lambda minus of 8, yes, 2 minus lambda square plus 2 lambda minus 8 is equals to 0 and lambda becomes minus 4 and lambda is equals to 2. So both are the distinct, right? Both are the distinct value or you can say eigenvalue, right? And therefore there is no problem. We have to only convert it to the diagonal canonical form. So the the and one more thing is there. The given model is in the form of given model is in the form of phase canonical form, right? Phase canonical form. So first of all, you have to convert it into the diagonal canonical form, right? Diagonal canonical form. And how it will be diagonal converted? So you have to find the p vector cp, you have to find the cp. So p vector you have to find out. And what is the p vector? P vector is nothing but eigenvector, right? So eigenvector corresponding to your eigenvalue. So first eigenvalue is lambda is equals to minus 4. Just calculate minus 4 minus 1 minus 8 minus 2 and x1 and x2. Just solve this equation. Minus 4x1 minus x2 is equals to 0, or you can say minus 8x1 is minus 2x2 is equals to 0. Both are the same equation. So simply you can write x1 upon 1, x2 is equals to minus 4, and your vector becomes 1 minus 4. 1 minus 4, right? In similar way, you have to compute the eigenvector. Eigenvector for corresponding to lambda is equals to minus lambda is equals to plus 2, and it becomes 2 minus 1 minus 8 4 and x1 x2 equals to 0 and 2x1 minus x2 is equals to 0, and the second equation is again x1 plus x2 is equals to 0, and both the equation again same, and hence you can write x1 upon 1 is equals to x2 upon 2, and the corresponding eigenvector is 1 2. So your p vector becomes 1 minus 4 and 1 2. Okay, so you have to find the p inverse also. So take the determinant of this equation. So I think this becomes 6, and you have to change this one. So 2 1 and plus 4 minus 1. Okay, so this is the p inverse. So if you find the p into p inverse, must become identity matrix, identity matrix will definitely come. Okay, when you solve. Now come to the p inverse ap, so that you can transform into the uh, diagonal form. So 1 by 6 p inverse 2 minus 1 4 plus 1 4 into 1, and A matrix is given 0 1 8 and minus 2, and P matrix is given 1 1 minus 4 2. Solve this, and if you find minus 4 0 0 2, so you can see here this is the eigenvalue or the represent to the diagonal form. Okay, and what will the CP? Because we have to check the CP matrix now. So CP matrix is nothing but the C matrix is 4 1. Okay, and P matrix is 1 1 minus 4 2. When you solve it, 0 6, and you can see here this is the 0 here. One column of this CP matrix is 0, and therefore this is not completely observable. Okay, one column. Okay, one column one column of CP is 0, and so that the system represented here is not completely observable. So I hope the fundamental of the Gilbert test, or you can say we are able you are able to understand, you are able to build up the concept of the Gilbert test for the observability, right? So that is all about the Gilbert test. In the next video, we will discuss with the we start with the Kalman test, and that's it. Bye.